Sam?
It lowers the activation energy for the reaction.
Good, and thus the reaction?
Well, have more energy to react.
Good, and goes faster. Right, so a catalyst goes faster. Remember we did the demonstration in the lab where I did it once and then the second time it like exploded because it went so much faster. Okay, so with equilibrium's interesting with a catalyst because it does make it go faster, but it's going to make it go faster in both directions. So if you want to grab some highlighters because yours is not colored, there are dots to show, but it might help to color it. You can kind of see on mine where the red is. The red line represents a catalyzed reaction, and the black line is uncatalyzed. So notice the difference here is that when you have a catalyst, we reached equilibrium, right, somewhere around 3 hours, because that's the point at which the red lines, right, notice that's where the red lines kind of plateau and don't change. But the black line, notice, is still changing here, right? And so it didn't get to equilibrium till about around 5 or 6 hours. So that's kind of the difference with the catalyst is you still get to the same plateau, but a catalyst will get you there faster. Okay, everybody have that filled in? Okay, we're going to skip all the way down now to where it says Le Chatelier's principle. And if you know how to speak French, you can probably say it much prettier than I do, because I don't speak French.
You should only let people with easy names decide.
Well, there's a problem with that, because of when America was established and we have much less history than these other places do. Okay, so here's our goal today, everybody. Le Chatelier's principle is the principle that tells us a reaction at equilibrium when stressed will react to relieve the stress. Today's goal is to get back to balance, which is why we're going to use balances to think about it, okay? Don't touch them yet. I'll let you in a moment, okay? But the idea is it needs to get back to balance, okay? Now, there's different types of stresses that can occur. There's 3. In this class, we're only going to cover 2 of them. We're going to be focusing on changing the concentration, which is like adding or removing something, or changing the temperature. By doing either of those things, it's going to stress the equilibrium, and it wants to get back to its ratio. Now, keyword here, it can't go back to exactly where it was before because you added something or you removed something. Like, it can't go back to the exact same place, but the ratio can be maintained. I will say this, that with temperature, the ratio actually shifts and changes, but you still get the equilibrium parallel idea, okay, where it can still get back to equilibrium. So today's lesson is about stress management, right? When stress comes into our life, we need to adjust, relieve the stress, and get back to homeostasis, right? That's what we do as humans, or hopefully you do, okay? Reactions at equilibrium do the same thing, okay? Once again, your answers are it's going to shift to the left, which means, label this here with me. So shift to the left means I'm making more reactants or products. Reactants. Okay, so those are one and the same thing, right? If I make more reactants, I'm shifting to the left. Okay, if I'm shifting to the right, then I'm making more products. And then sometimes maybe the stress didn't actually stress it at all, and so it doesn't need to shift. Right? Sometimes things can be done that don't cause it to change. Okay, so let's start with concentration. So once again, concentration is an amount. So what I'd like you to do with your scale, okay, so this is like a mathematical scale, right? So you have to add up, I'll get you guys one, right? So both sides have to add up to the same sum to be balanced, okay? You come up with whatever equilibrium system you want under these conditions. You need to have at least 3 tags, that's what I'm calling these little blue things, on each side. If you want more than that, that's fine. But everybody, I'll give you 1 minute, make your own equilibrium so it needs to be balanced in whatever ratios you want. Ready, set, go. Okay, make an equilibrium. Minimum of 3 tags on each side. Okay, but it just needs to be balanced, whatever that means.
Times by 3.
Yeah, they're a little... Yeah, don't be too aggressive or they all can just fall off. Have a smiley face. Good job. Are we balanced over here? Some of them are slightly squampus, so they don't like completely. But have a smiley face. You are not balanced. Get to equilibrium.
We are going to.
I think we're there. Are we there, or is it just?
No, we can't.
That looks nice. Have a smiley face, you guys. Good job. Are we there?
Well, guys, you're just putting stuff everywhere. You gotta. What's the number? How much is it added up to?
17.
Have a smiley face. Are we there? All right. Have a smiley face. Are we there? Some of them are a little like, but does it balance? Is the numbers add up actually? Okay. Have a smiley face. Okay. What are we doing? Get back to equilibrium. You messed it up. Get back to balance. Wait, don't touch it once you get to equilibrium. Hands off. Okay, have a smiley face. You're there now. Okay, stop touching it. Unless those that need to fix it really quick. Get to equilibrium. Okay, eyes back up here. Eyes up here, everybody. Thank you. Hayden Jones. You have an appointment at 8:45. Okay. Now, eyes up front here, everybody. So with our scale models, once again, this is a way you can think about the balance of equilibrium. When I learned about equilibrium, and honestly, I can't even remember if the scale something was, I don't know if it was taught to me or if my brain, or I don't know where it came from, but I continue to use it. Okay? When I would do problems in college that dealt with Les Chateliers, I would hold my hands like this, pretend I was a scale to help me think through them, because I'm just a very visual learner. Right? So today you can use them as you're thinking about it, and then if that continues to help, right? Like so. Now, your system's at equilibrium. Okay, everyone eyes up here. Your system's at equilibrium. You right now are an outside influence. An outside influence is going to take a tag. Everyone take a tag from the bottom. One tag. Okay, now the one thing, and I need to put labels on this because you're like mirroring each other. So it's a little bit like one person's left is the opposite of the other side. So I need you to decide right now, one side needs to represent the reactants and one side needs to represent the products. Decide for your group which side's which. Okay, I'm going to make little like signs for them eventually. But.
Okay, which do you want to be reactant? Like which side? Yeah.
Okay, did everyone figure that out?
Side B.
Okay, when I model it here, everybody, eyes up here again. Okay, I'm going to model as if, like, the reaction's above my head. So this hand's always going to be the reactants, because the reactants are on this side of the arrow, and this one will always be the products. Okay, so we're going to add a tag to the reactant side. So go ahead and stress your system. Go. Just add one and then don't touch it. Put it on and then hands off. I should see everybody's getting stressed.
So stressed.
So a tag to the bottom and add it to the reactant side. Okay, good. Okay, stop touching. All right. Okay, so right now our system is stressed. It's not at balance. To get back to balance now, the system, so when I say the system, that only applies to the tags that are on the bar. The system cannot use the tags at the bottom because that's an outside thing. It's not like a reaction can reach out to the universe and say, I need more of you, bring me into this beaker, right? But the beaker, the reaction can move things from reactant to product and product to reactant. Okay? So I'm going to give you 30 seconds. The system, get it back to equilibrium, ready, go. But don't use tags from where? The bottom. So it should be, you got to get it stressed first. So you should have taken one from here and added it on to stress it.
Stressed it.
Now you got to fix it, but you can't use anything not on there. Does that make sense?
We can put one.
Good. Have a smiley face. We're back to equilibrium.
What if you?
I don't know where my
It has to be tempted. You can't
Good job. Back to equilibrium. Back to equilibrium. We're back. Are we back? You guys are not back to equilibrium yet.
It equaled the same thing before, so how can we equal the same number now? Additional ones add. Yeah.
So where did you add one?
6.
Okay.
So it's 26 to 20.
Okay. So it wants
Add some
to.
to this side?
Yes.
Oh, I didn't know.
Because reactants can turn into products.
Okay, guys, let me.
There you go. Okay, eyes up front here, everybody. All right, Kate, I'm going to pick on you because I know you guys got there. So I think I saw it happen, but just to confirm. So Kate, to get it back to balance, which you'll eventually get there, but what had to happen? What did the system do?
We had to move some reactants to products.
Ice cream. So, which I saw, right, you had to move some of the reactants and turn them into products. That would be classified as shifting the reaction to the right because you're making more things on the right by using the things on the left. Okay? I want you to write a sentence next to this word where I put that arrow right there just to clarify. So when we say shift to the right, this means, or I guess you could kind of connect it. It's up above. This means more products were being made from the excess reactants, right? The stress was there was too much reactants. So to get back to a state of balance, we had to use those excess reactants to make more product. This is the whole idea of Le Chatelier's principle. So anyone by raise a hand, so this was an example of increasing. Can anyone by raise a hand tell us what they think would happen if we were to remove one and then it has to fix itself? What's going to be the difference? If I added, it went the opposite way because we had excess. If I remove, good. It's going to need to go back to refill in what was taken out. Have a smiley face, Creighton. Okay, so that's what our next one says here. Okay, skip that practice problem and find the word where it says the forward reaction is also favored if the products are decreased. So it's down where it says concentration continued. Everybody see that down there? We'll come back actually to the practice problem, but. So skip down to where it says concentration continued. So if it is decreased, then it's going to shift in order to refill that amount back in. Now, one formality thing that's a little new this unit, just by chance, this right here, brackets, oh, that highlight did not show very well on the blue. Brackets are a symbol to mean concentration. So if you see something like this written in brackets, okay, this is a symbolic way to say concentration. Okay, so just FYI, it's kind of, we haven't seen that before, but brackets are a way to represent concentration. Okay, questions so far? Okay, we're going to go back up to that problem right above it and try. I'm going to do these ones together, and then I'm going to have you try some to check our understanding. Okay, so this tells us that the O2 concentration is doubled. So the first thing is to identify what is O2. Is O2 a reactant or a product? It's a reactant. Okay, I guess I shouldn't put a down arrow because we're increasing it, right? So O2 is increasing an amount. If I add reactant, then it needs to go the opposite way to rebalance out the scale. So this would shift to the right, right? So go ahead and fill this in with me. This is a practice problem right above where I wanted to finish the notes before we did the practice problem. Okay, so the stress was we added more reactant, and so as a result of the stress, it needs to make more product. So then the second part of the question says, this means that the concentration of SO3, so it's related to that stress, so since SO3 is a product, and I'm shifting to the right, that means the concentration of SO3 will increase, because I'm making more product. So once again, the answers should be linked. It would be like you're never going to have a situation where you shift to the right and the products go down. That just doesn't make sense. So keep in mind, like it's really the same answer, just different ways. And I believe these two got left off your paper. So if you're looking for them, they're not there. Okay. Questions so far? Okay, we did this one. Okay. Skip down to where, I think it's the top of the next page. Yep, so turn to page 6. I'm going to have you guys try these ones for 5 smiley faces, and then we'll check it to make sure we're on the right track. Okay? You can work as a table. Ready, set, go. All right, 3 minutes and we're checking it. To get the smileys, they have to be written on your paper. Like, yeah, I have to see an answer to get the smiley face.
Should I take everything with me too? It's a Wednesday.
Yes, I would, because the bell will ring like 5 minutes later or so.
Okay. Jamie, if I leave at 8:40, am I okay?
Yeah, that should be fine.
You would love it.
So if a product is increased, it shifts left. If reaction is
Opposite, yes.
Because additional SO3 is added.
Give me a pencil drop if you're done. That way I'll know if you need more time to think.
Oh, we're on the wrong one.
That is not good.
Find a dry out.
We don't double stack.
Are you for real?
Yeah.
On this fourth one, would it shift left or right?
So what is SO3?
It's a product.
So if I add product to get back to balance, what do I need?
Oh, to get back to balance. Shift to left. Yeah.
So you're always answering to get back to balance.
I wasn't right.
Oh shoot, that's the
Thank you. Okay, everyone put your finger in the air. Pick your favorite hand and put it in the air. Finger in the air, everybody. Put your finger in the air. Okay? What you're going to do is, and I'm going to have you close your eyes so you're really not influenced by others. Okay? So what you're going to do is close your eyes. Well, I guess check what your answer is. So we're answering the first one. Okay, so if SO2 concentration is decreased, what is the reaction going to do? So you're going to point, if you think it's pointing to the left, point to the wall. If you think it's shifting to the right, point to the window. All right, fingers up, eyes closed. 3, 2, 1, point. Good. If you're pointing to the cupboards, have a smiley face. You're correct. We're like 90% there on that one, so that's good. Okay. Now, we're going to point up or down for increase or decrease. So point your finger, I guess, sideways. Okay, ready? You're going to point up or down here. Ready? 3, 2, 1, point. This means that the concentration of SO3 will increase. Because shifting. Wait a second. I'm turned my left and right, so I really struggle with sometimes. Okay, so for this one, we added SO2. Did I say right or left? Did I say cupboards? We decreased. Sorry, thank you. That's why my brain's backwards. Okay. Oh dear.
Wait, so.
You got it right? If we said decrease?
Back up here. Okay, so this decreased. Oh, that's an eraser. Right? So to get it back to balance, I drew my arrow the wrong way. That's why I'm confusing myself. I said the right thing, but I wrote the opposite. Okay, so since that decreased, I needed to make more reactants. Everyone good there? Which means my product needs to decrease. We got there, friends. Okay, questions before we try the next two? Okay, fingers up, number 2. Fingers up, number 2. On the count of 3, point which way it's going to shift if O2 is added. Mine says 2. I think yours just have dots. So number 3, dot. Okay, 3, 2, 1, point. Very good. If you're pointing to the products or to the right window, have a smiley face. Which means what's going to happen to our concentration of SO3? It should increase. All right, questions on any of these questions? Did you have one more? I feel like you have more dots than I have. What did we miss? Is it a whole nother question?
I think so, yeah. This one.
Oh, yeah. Okay, so the next one is, left off of mine, if SO3 is added. Okay, so this is your next one. Fingers up in the air. Oh, did it just... Is it there? Oh, it is there. I just can't read. And didn't go down. Okay, so if SO3 is added, I thought that was an increase, decrease one. Point with your finger, ready? Hands up. I need to see everyone's hands up. Everyone put your hand up. On the count of 3, point to the window or to the wall. Which way is it going to shift? 3, 2, 1, point. Hold still so I can get a quick screenshot here. So since SO3 is a product, then that means I need to make more reactants. So if you're pointing this way, have a smiley face. Right? If I add product, it's going to make more reactants.
Is this the left?
This is the reactants. If that's easier to think about than left and right, but it would be the left. So. And then your final smiley face, you should have said SO2 would decrease. Oh my gosh, I can't handle this left and right thing either when I'm facing you. I'm going to have to teach like this. Like left and rights have been the struggle of my life.
Wait, so it's increase?
Yeah. Okay, any questions on concentration shifts? Okay. Okay, skip down. I think it's right below it to where it talks about temperature. Okay. Now, the nice thing is, everybody, temperature should go quicker because it's really the same concept. The catch is you just need to know if the reaction is exothermic or endothermic, because that changes what side the heat is on. But that's going to be given in the problem somehow. But other than that, it's really going to be the same idea, where if heat is a product and you increase the heat, then it's going to shift the opposite way and make more reactants. And vice versa if the heat is a reactant. So really, you can still think of it like a scale even when you're dealing with temperature, because heat is going to be focused on one side for endo versus exo. Okay, does everyone have those filled in if I go to the next one? Okay, so looking at this example, everybody, what I want you to highlight here, okay, is highlight this kilojoules, 92 kilojoules. This is a way to show heat. Sometimes we write the word heat, sometimes we write the value of the heat. Either way, the key component is the heat a reactant or a product in this equation? It's a product, and so you just treat it the same way. Okay, so if I'm reactants and products, if I add more products, which way does it need to shift to get back to balance? To the left. Yep. Because once again, the temperature is impacting the product side. And so it has to go the opposite way that it was impacted. And then obviously decrease would have the opposite effect of shifting to the right. Questions on the difference between temperature and concentration? Yeah.
So are we adding heat?
In this one, so the first one was increasing temperature is like adding heat.
Oh.
Decreasing temperature would be like removing heat.
Okay.
Does that help?
Yes.
Yeah, so it won't typically say add heat, it'll say increase the temperature.
Okay.
But it means,
So if it's exothermic, then wouldn't it be, if we're adding it, wouldn't it be like releasing it?
it's the thing of the heat always impacts only one side when it's exothermic. So when it's exothermic, adding the heat only adds to the products.
Okay.
So that's why I would always go to the reactant.
Okay.
It is a little weird because exo do release heat, but if I do it in like a hotter system, that heat's gonna push it the other direction.
Okay.
Does that make sense? Okay. All right, any other questions before I have you try the last practice problem there at the bottom? Okay, try this one for 3 more smileys and then we'll check it. Ready, set, go. Try these last 3 for 3 more smileys. Give me a pencil drop when you're done.
We have to do the opposite.
I put endothermic to the right.
I put all the
So on,
Heat increases, so this gets more.
so on this one with the shifting, so which side is the heat on in relation to the arrow?
This one will stay the same, right?
Is it on the left or the right?
The right.
So keep in mind, your answer is always how to rebalance it from the stress. So if I add to the right, which way does it need to go to get back to balance? There you go. Does that make sense?
Yeah.
So don't answer like what the stress does, answer how to fix it. So then, if I'm shifting to the left, let's check this one here.
Or
There you go, good. So at least those two, you had the same You had the correct logic in your pairing, so that's good.
Yeah, it wouldn't. Why?
Sorry, I was trying to get them.
So your answer to 2 and 3 Jackson don't match.
Okay.
Because you're saying you're going to shift to the left, and what side of the equation is SO3 on? So if I look at the equation, what side is SO3 on?
On the right.
So if I'm shifting to the left, something on the right can't go up. Does that make sense?
Kind of.
Because if I'm going this way, these things are getting made and these are getting used. It's like taking from this side of the scale and moving them over here. So one of these is right and the other is the opposite. So think about that real quick and see if you can figure it out.
That was really funny. We need to find a
So do y'all have the same answer?
I don't know if they've done
Okay.
Talia hasn't done it.
So these two aren't logical. Because if you're shifting to the left and SO3 is on the right,
Oh, I wasn't sure
no,
if that
not
meant
that.
like if the temperatures increase like this whole side increases or if it's just the temperature.
See, I don't
it
know.
affects, think of it as affecting the product side. So to get back to balance, which side do I have to go to?